All right, folks, here we go. We're getting more into this kinetics. I'm real excited about this stuff. So as you can see, I've got the Math 3 model up here, all right? And so I'm going to kind of be teaching side by side with these things. I'm going to work out, the equations on my board here. And then I'm going to be showing you how it connects to these models that you're doing, all right? And some of the things, some of the examples that I'm going to show you here are a little bit more detailed than what I'm asking you to do in the assignment. So I'll point that out when I've added things to this Math 3 assignment that you're not required to do, okay? So let's get into it. So first order reaction. So in a first order reaction, and what we need to assume here for now is we're not really calling this a mechanism. We're not really calling this a total step. We can just think of this as a very simple elementary step, a fundamental step, okay? And so for a first order reaction, we could say that A goes to products at rate constant K. Okay, so you can see here on my Mathematica model, I just said A goes to B with rate constant K. Same thing as just saying A goes to products. Okay, and so we're saying that we know that this is a first order reaction, or we're imposing it's a first order reaction. Okay, so when I go to write the rate law of this reaction, that's the first way that I start. Okay, I start by saying dA by dt. And when I consider the stoichiometric coefficient, right? Remember, we did all of that stuff, if I back up for just a minute, right when we talked about these relative rates, technically the reactant should be negative dA dt, right? So let's put that in there. Okay, here we go. So I'm going to say negative dA dt equals, and it's going to be the rate constant times the concentration of A. And since we're saying we know this is a first order reaction, we know that this is really A raised to the first power, okay? So now so this is my rate law, okay? And this is a differential equation, believe it or not, all right? So if I rearrange this, and I'm gonna write this as dA dt equals negative K times A, all right, so if I call T equal to X and concentration equal to Y, just to make this a little bit simpler to view, then this is a differential equation of the form dy dx equals negative K times Y, okay? And as it turns out, we can solve this. I'm going to solve this equation next, okay? But as this becomes more complicated, as we build in more complicated reactions, we can't solve these types of differential equations with an analytical equation. We have to do a numerical solution. And I'll explain that into the Mathematica file soon here. Okay? So another way that I could write this, just to give us some familiarity here, if we know that y is a function of x, I should say. Actually, yeah, let's make sure that I'm consistent. Just using my simple notation to indicate that this is a differential equation, then I could rewrite this as y prime of x equals negative K y of x, right? So I can write this in the same way, where dy dx is the same as saying y prime of x equals negative K times y of x. Okay, that's what makes this differential. So now going back to this, if I want to solve this for the integrated rate law, then what I need to do is get the like terms with the like terms. So I'm going to move A next to dA, right? So that's going to go dA over A. And I want to integrate that from the initial concentration, A0, to the concentration at any time t. It could be the final time, but we're just going to say generic anytime t, okay? And so that's this side. And so I just divided A over to this side, and now we multiply dt over to this side, and so that becomes the integral from 0, right, A, 0 times 0, to just t. We're integrating it from 0 to any arbitrary time t, and that's going to be negative k dt. Okay? So this is a very easy differential equation to solve. So we're basically, right, if you notice here my line, these are all the same equation. It's just writing it in a different notation. Okay? So now I can solve this all day. I know the integral of this side is the natural log, and when I apply the limits, that's going to be the natural log of a at time t over a initial. And the integral from 0 to t of negative k dt is very easy. That's just negative k times t. Okay? And so now I can rearrange this in several ways, and I'm going to write all of those down right here. So several ways to write the first order integrated rate law. So I'll start by rearranging this one. And when I rearrange that, I get the natural log of a at time t. And I'm going to do a couple of steps here, okay? So I'm going to separate these out because I know that I can write the fraction as a subtraction for natural logs, right? And so that still equals negative kt. So rearranging further, if I say natural log of a at time t, that equals negative kt plus the natural log of a0. And now if I were to plot the natural log of a versus time, I will get a straight line with a negative slope. And the slope of that line is the rate constant. Okay? So we always view rate constants as positive. Rate constants are always positive, but because of the negative sign in that equation, there's a negative slope. Okay, so this becomes a y equals negative mx plus b, right? And the fact that this is decaying tells us the reactant's concentration is decreasing in time. Okay, so now there's another way I can rearrange this equation, and I hope that I've given myself enough room here. So I'm going to take the e of both sides, and when I do that, I get, so let's box these things up so we know which equations we want. So this is a good equation to know for first order. Okay, the linear form. All right. And now the form that I like to use more than the linear form, so if I take e of both sides, right, then I just simply get at over a0 equals e to the negative kt. Okay? And what I really like about this equation here, man, I'm getting sloppy with my work. Sorry, folks. There's another way I can also rearrange this, like the following: at equals a0 e to the negative kt. Okay, so both of those are acceptable. And what I really like about this one with the at over a0, those become relative concentration units. Okay. So man, oh man, oh man, I was too sloppy writing my notes. Okay. So basically, in other words, at time 0, at the start of the reaction, this ratio will be 1.0, right? Because at time 0, AT is the same as A0, the initial concentration. So I really like this because you don't have to know the absolute concentration. And as you'll see in experiments, this is really useful. So you don't have to have a calibrated determination of concentration if you can determine the relative concentration.